Hello everyone, I am Dr. Kiranmayi, Area Chair and Assistant Professor, Digital Transformation and Operations, School of Business, Aditya University. This present lecture is the continuation of the previous lecture in which I have discussed about how to solve the linear programming problem using Simplex method. There I have discussed how to transform the given LPP into standard format and how to set up the starting Simplex table and how to find out initial basic feasible solution IBFS and checking whether this IBFS is optimum solution or not. So, this is discussed in the previous lecture. And in this present lecture, I am going to discuss how to find optimum solution using Simplex method. So, for this problem, we have set up the starting Simplex table and found IBFS, and it is observed that that IBFS is not optimum solution. This is the starting Simplex table which we have set up in the previous lecture. From this, we can understand that this is the S1 is the outgoing vector and x1 is the incoming vector. Okay, if all the delta j's, all these net evaluations are positive, then the IBFS is considered as optimum solution. Since here we have negative delta j's, therefore the solution is not optimum solution. This S2 must be replaced with this x1 like this. So, S2 is replaced with x1, and after that the value of x1 in the objective function, the coefficient of the x1 in the objective function is 13, that is to be mentioned, that is represented here as 13. Coefficient of x1 in the objective function is 13, that is to be written here, and S1, S2 coefficients in the objective functions are zeros, therefore here 0. Okay, and after that we have to make this unit element, this pivot or key element into unity. How can we make this 5 into 1? If we divide 5 with 5, it becomes 1. So, in order to maintain the entire row value as constant, so entire row must be divided with 5. So, 5 by 5 is 1. If 3 is divided with 5, it is going to be 3 by 5. 0 by 5 is 0. 1 by 5 is 1 by 5. 1575 divided with 5 is going to be 350. So, this is how we have to transform the key element of the key row like into unity like this, and after this the other elements apart from the key element should be made as zeros. 4 should be transformed as 0, 1 must be made as 0. How can we do it? By using elementary row operations which we use in matrices. So, by using those row operations and using this new R2, we have to change this new element 1. Using this new key element 1, we have to make this 4 as 0. So, here we have 1 and here we have 4. So, if this 1 becomes 4, if we subtract this 4, it becomes 0. Therefore, what I do is, I will multiply new R2 with 4 and then it becomes 4, and if I subtract this 4 from it becomes 0. Therefore, 4 into 1 4, 4 minus 4 is 0. So, I have written here 0. If it is multiplied, this 3 by 5 is multiplied with 4, that becomes 12 by 5, and this 12 by 5 must be subtracted from this 5, that is 5 minus, that is 5 5 is 25, 25 minus 12 by 5, it is going to be 13 by 5, and then next 0. So, 4 into 0 4, 1 minus 0 1, so 1 we have written, and then 1 by 5, multiply this 1 by 5 with 4. Okay, if we multiply 1 by 5 with 4, it becomes 4 by 5, and here it is S2 0 minus 4 by 5 minus 4 by 5. Here it is 0, no, from this 0 we have to subtract this 4 by 5. So, minus 4 by 5, and likewise this 1500 also, here we have 315. So, multiply 315 with 4 and subtract from 1500. So 1500 minus here we have 315. We are multiplying with 4. Now it will be 240. So this is how we have to make the element in the key column other than key element as 0 by using this first row operation. And also likewise the other element in the key column, that is 1. 1 also must be made as 0 by using this one. Here it is 1, here it is 1. If we subtract both elements, it becomes 0. That is why I am changing this R3. This is third row. This is R1, this is R2 and this is R3. And this one, if I subtract 1 from this one, it becomes 0. Therefore, I am changing R3 as R3 minus R2 new. Then it becomes 0. Remember, always these row operations must be done along with the new row which consists of unity, which we made as unity from the previous table of key element, right? So, these are the points to be noted. So, by using this second row operation, this third row can be transformed like this using this row operation. And after that, the next thing, after transforming all the elements like this, after making the key element as 1 and other elements as zeros, and then the next step is to calculate performing the net evaluations. How can we perform these net evaluations? Here x3 is 13. I will show you. So, first one, for x1 let us calculate net evaluation. How can we calculate? Coefficient of the basic variables in the main objective function should be multiplied with respective elements in that column. Okay. For x1 I am performing net evaluations. Therefore, 0 into 0 plus 13 into 1 plus this 0 into 0 again 0, and this is going to be 13. And this 13 must be subtracted with the corresponding x1 initial coefficient value is minus 13. So, 13 minus 13 is going to be 0. Therefore, the net evaluation for x1 in the first iteration is going to be 0. And after that, for x2 also we have to perform net evaluation. How can we find out? Like x2, the elements in the x2 column must be multiplied with these values of the basic variables, multiplied with 3. This one, 0 into 13 by 5 plus 13 into 3 by 5 plus 0 into 7 by 5, and 0 into 13 5 by 0, 13 into 3 by 5 is going to be 39 by 5, and this is 0, and the ultimate value is 39 by 5. And from this, the corresponding x2 coefficient is minus 11, 32 minus 11, and this value is going to be minus 16 by 5. So, this is how we have to perform. We have to calculate the net evaluations for all the variables. Now, we also should find out the z value. How can we find z value? Here x value is 13. 0 into 240, 0. 13 into 315, 0 into 105, 0 into 105, 0, 0 into 240, 0, 13 into 315 is 4095. So, this is the value of z in this iteration, and x1 is 13. This is the solution of the given LPP in the first iteration. Now, we have to check whether this solution is optimum or not. How can we check out? Look at the ZJ values, net evaluations. So, if all the net evaluations are positive, this solution is optimum solution. But see here, one net evaluation is negative. It indicates that this solution is not optimum solution. Therefore, if the solution is not optimum solution, again we have to move on to the next iteration. So, this is the simplex table of first iteration which we have done previously, and we have again the same process we have to use. So, first we have to identify the key column. So, how can we identify key column? the most negative net evaluation. So, which is the most negative? This is the only negative value. Therefore, this column is going to be key column. So, first we have to find out key column in this way by considering the most negative value of the net evaluations, right? And after identifying the key column, the next step is to identify the key row. So, how can we identify key row? Using minimum ratio. So, we have to calculate minimum ratio using the formula xb by xk. That is, this is xb solution matrix, this is xb, and this is now key column is the second. This is going to be the key column now. Okay. Therefore, we should calculate this minimum ratio like 240 by 13 by 5, which is 92.3, this one, and also 315 by 3 by 5, which is 525, 105 by 7 by 5, which is 75. So, this is how we have to calculate minimum ratio in order to find out the key row. So, after calculating the term itself suggesting minimum ratio, among these which we have to consider minimum value, it is 92.3, it is 525, it is 75. It is the minimum ratio. Therefore, this third row will be the key row. The element of intersection of key column and key row is this one, 7 by 5. This is the key element of this iteration. And now, this key element again should be made as unity like this one. 7 by 5 to be made as unity, and the other elements in the key column must be made as zeros by using elementary operations as we discussed in the few minutes before. Okay. And using those operations, again transform the key element and other elements in the key column as zeros, and also perform the net evaluations. And after performing all those, again here the solution is x1 initially it is 13, x2 coefficient is 11, okay, right here 11, and here the value of x1 is 75 and x2 is 270 and z value is 4335. And now we have to check whether this solution is optimum or not. How can we check out? Look at the net evaluations. Here all the net evaluations are positive. Therefore, the solution here x1 is 270, x2 is 75 and z value is 4335. Therefore, the solution here is x1 is equal to 270, x2 is 75 and the solution is 4335. It is optimum solution based upon the net evaluations. All the net evaluations are positive. Therefore, this is optimum solution. So, this is how we can find out. Therefore, this is how we can use simplex method to solve the linear programming problem. So, in this lecture, we have understood how to move to the next iteration and how to reach optimum solution, how to check the solution is optimum or not, and how to find out the optimum solution using simplex method for the linear programming problem. Thank you.